This video provides information on load duration curve analysis. Much of the information provided here is extracted or taken from EPA document on load duration curves. Load duration curve analyses provide the ability to relate water quality concentrations in a stream, or which would be, let's say, milligram per liter, or loads in a stream, such as kilograms per day, and how those values differ depending on the type of flow that's occurring, low flow or high flow, drought flow, storm flow, let's say, in a stream. It provides a display that shows a relationship between flow and loading capacity. Loading capacity here would relate to water quality impairment, and means that if the water quality load or concentration is below a target value, then the stream is not considered to be impaired. Otherwise, if it's above that target value, then it is considered to be impaired. And the conditions, the flow conditions where that impairment occurs, can be observed in a load duration curve analysis. Load duration curve analysis provides the ability to see how water quality is affected by flow magnitude, but also by time of year or season of the year, because there are variations in water quality depending on the time of year. It provides a link between the concerns on water quality and how those water quality effects are related to key watershed processes. And here the watershed processes would refer to flow processes or runoff processes associated with surface runoff because of storm flow, drought flows, which would be more associated with groundwater discharge in the stream, or intermediate type of flows, such as flows from drain tiles or shallow subsurface flow. The analysis does not by itself account for fate and transport mechanisms in a watershed, because one is not looking at the details of what's going on inside of the watershed. And when you are doing a load duration curve analysis, you're only taking data at the outlet of the watershed, the data being the flow and pollutant concentration. It is assumed in load duration curve analysis that the primary driver of the water quality variation is the flow. And of course, if other processes are affecting the water quality variation, then one needs to use other assessment methods in addition to the load duration curve analysis. Here's an example of a flow duration curve, and the flow duration curve is the foundation for the load duration curve. This is an example for Salt Creek near Greenville, Illinois. Flow data, daily flow data, daily average flow data, let's say, for that river, are taken and analyzed in a way to relate the probability of exceedance of a given flow rate to the magnitude of that flow rate. And what's shown here is the flow duration curve. The highlighted number, the discharge of 440 cubic feet per second, that interpretation of that number is, for this graph, is that 60% of the time, the discharge in any given day in that watershed, the discharge will exceed 440 cubic feet per second. If I take another example off of here, the one marked as 130 cubic feet per second. The interpretation is that 90% of the time, that is 90% of the days, 130 cubic feet per second would be equaled or exceeded on any given day. And for the one that's 10%, the discharge is 3,270, which means that 10% of the time, the discharge, or 10% of the days, the discharge will equal or exceed 3,270 cubic feet per second. Now, the shape of the flow duration curve is greatly affected by the source of the water, whether it's more surface runoff, overland flow generated runoff, whether there's a lot of lakes and wetlands that are contributing to the flow in a stream, or whether it's more groundwater driven flow in the stream, has a complete or a very big effect on the actual shape and slope of the flow duration curve. The climate, of course, has a very big effect as well. In a dry area like New Mexico, one can easily have times when there is no flow at all in the stream. We even see this in Minnesota in some streams like Minnehaha Creek. What's shown here is that for a large fraction of the time there is no flow. About 54% of the time there is no flow in this stream channel, and 46% of the time the flow equals or exceeds 0.1 cubic foot per second. All right, so for construction of a load duration curve, because the flow duration curve is the basis for the load duration curve, the one of the aspects, or one calculation that is done, is to determine the loading capacity of the stream. And here the loading capacity is defined as being the target, or associated with the target water quality concentration. The numbers that are used to derive this curve are taken directly from the flow duration curve. The flows at any given percent level are multiplied by the water quality target, and then a conversion factor is used to give the correct units for the load. So here the percent levels that are derived from the flow duration curve are plotted against the load, in this case for nitrate, of tons per day. So for the one that was 60%, the discharge was 440 cubic feet per second for Salt Creek. The EPA, or the U.S. national standard for nitrate, is 10 milligram per liter. So we multiply the flow times the concentration. That should give us load. To get it into the correct units, we have to use a factor which converts the units to the ones that we want to use, in this case tons per day. So for that, the factor is 0.002695. So for that discharge with that water quality concentration, the load is 11.86 tons per day. What would be said here, or what would be interpreted here, is that 60% of the time the nitrate load in this stream would equal or exceed, on any given day, 11.86 tons per day. That is, there would be a 60% chance, or 60% of the days, the nitrate load will exceed 11.86 tons per day. The shape of the brown line here, the load duration curve, is exactly the shape of the flow duration curve. It's just scaled on the vertical axis. So construction of the load duration curve is very easy. That is, the target load duration curve is very easy once you have the flow duration curve. A definition of loading capacity, EPA defines this as being the greatest amount of loading that a water can receive without violating the water quality standards. So as long as the loading is less than the loading capacity, the assimilation capacity of that water body, the stream will not, or the water body will not be considered to be impaired. All right, so now we have a target low duration curve, and on top of that same graph, we want to plot the actual sampled data, and this graph has a lot of information on it. The brown line is the target low duration curve, and that would be based on some standard. In this case, we're looking at fecal coliform bacteria, which would be measured in terms of number of colonies per liter, and the load would be expressed as number of colonies per day of the fecal coliform. The numbers that are given here are very large, 10 to the 13th, 10 to the 14th, and so on, as you can see on the vertical axis. The individual diamonds are data points that are collected from grab samples of fecal coliform bacteria. The grab sample is taken, and also a flow measurement is made so that one can then calculate for that, using that flow and the concentration in the grab sample, one can calculate the load associated with that. And these are plotted on the same graph as the target low duration curve. Now there's different, different data points are distinguished from each other based on time of year, and based on the type of storm, or based on the contribution of storm flow to the stream or to the water body at the time when the sample is taken. So the diamonds with a plus inside are ones where the sample was taken in the period from April through October. The ones with the red diamond on the inside are ones in which it was estimated that storm flow was greater than 50% of the total flow in the stream at the time. And we can see that many of the data points that have the red diamond on the inside are the ones that are above the target low duration curve. Data points that are above the low duration curve, the target low duration curve, are considered to be in violation of the water quality standard, or in exceedance of the loading capacity of the system. Ones that are below the low duration curve, the target low duration curve, are considered to be in compliance of the loading capacity. Other things that we see on the graph here are that one thing that wasn't mentioned before is that generally we break up the graph into different flow categories. Here the EPA recommends low flow, dry conditions, mid-range flows, moist conditions, and high flows. And the percent levels associated with each of those is the standard that the EPA recommends. So their points that all fall within the high flow are grouped based on that hydrologic condition of high flow. Within any one of those flow conditions, we see that the data points can be analyzed and statistically, and the plots that are shown there are called, the boxes that are shown are called box and whisker representation of the data. And what's shown there, in each box, we've got three horizontal lines. The upper and lower lines of each box is usually the 75 percentile or quartile and the 25% quartile. And then the middle line would be the median of the values. Those are values that are derived from the grab sample values within any one of the hydrologic condition regimes. And this is these are called the zone patterns, the loading characteristics within any one of the given hydrologic conditions. These data can then be used to derive a total load, in this case a fecal coliform on a daily basis or on an annual basis for the entire flow regime, for the entire graph, considering all hydrologic conditions. Generally, when one looks at this kind of graph, you can see that there are some violations, but the environmental agencies are not so strict to say that if just one violation occurs, you've failed. The system is in non-compliance. Generally, an agency would say that, well, if, let's say, 5% of the values fall above the target, then we would consider the system, the stream or water body, to be impaired. The actual percent that one would choose there would depend on the agency. So you might use 5% and you might use 10%, let's say. So the hydrologic conditions that are shown in the flow and load duration curve, the zone patterns, the effects of season or storm flow effects are important in interpreting what's going on inside a watershed. It helps one to maybe determine what the sources of the pollutants are based on just knowledge about the hydrologic and transport processes that are occurring inside of a watershed. Here are two simple interpretations. One is that one would expect that at low flows, if you have violations of the standards, these would generally be associated with drought flow conditions and would indicate that maybe it's because of point sources of pollution, maybe a pipe outfall, or it could be failing septic systems. If you're looking at sediment, generally sediment loads would be really low at low flows, just because sediment is usually generated in the stream during high flow, either intermediate or high flow events. In contrast to that, at high flows, generally these violations would indicate that you have non-point sources that are contributing to the violations, because these would generally be associated with surface runoff processes. So high fecal levels might be associated with confined animal operations, could be runoff from city streets or sidewalks where pets, maybe the neighborhood is not going around, people are not going around and picking up the poop from their dogs, for instance. So it would be from surface runoff processes would be generating these violations. And when it comes to sediment, generally sediment loads will be high during high flows, because you have overland flow during high flows, and you also have stream bank failures during high flows, so you'd expect that sediment loads will be higher at that time. All right, so now this is the last slide I'm going to show in this section. Here we can use the load duration curves to develop a TMDL, and I'll show some details of that in the next video. The TMDL equation that you've seen already in the class, TMDL is the total maximum daily load, and it's equal to the sum of waste load allocation plus the sum of the load allocation, which is really the non-point sources, and then plus a margin of safety. And the TMDL can be expressed in terms of mass per time, let's say kilogram per day. Can be expressed as a concentration for some things, such as oxygen. You might want to use concentration, or BOD, which would be biological oxygen demand, or other units could be used as well. So with that, I'll stop this video and we'll move on and look at what the margin of safety is in the next video.